Hello, my name is Brian Black. I'm one of the principal architects as well as the technical evangelist here at Deep Instinct. And today we're going to be going through the differences between deep learning and machine learning. Deep Instinct, of course, is built entirely on a deep neural network, and that produces an artificial brain, which allows us to solve threats in zero time. So let's kind of go through and talk about the differences in artificial intelligence and the fundamental differences between machine learning and deep learning. So to begin, Deep Instinct was founded in 2015. And I really kind of want to focus on that registered patent because it's really, really important. When we start talking about deep learning, the framework of deep learning is really what gives credibility and capability to an artificial brain. And it's important to note that here at Deep Instinct, we are not using an open source framework. We've actually custom built our own framework from the ground up, patented specifically for cybersecurity. So as we kind of go on, keep in mind that the framework that we're talking about, the capabilities of Deep Instinct, are going to be extremely difficult for any other vendor to challenge or any other vendor to duplicate simply because of how we built the neural network. So what is deep learning? Artificial intelligence came about really around the 1950s. We started to see the rise of the first computerized artificial intelligence. But let's talk a little bit about what AI really is. AI, very simple definition. Can a computer do a thing independent of a human? That's it. So by that very definition, legacy AV, legacy antivirus is considered AV, is considered AI, because what does it do? It spends its time looking at patterns on a network or on disk, and it makes decisions based upon its signatures, based upon its programming, independent of a human. But I don't think anyone would call their AV advanced artificial intelligence. So we start to think of artificial intelligence in a more grandiose capacity around 1980 and beyond. This was the rise of machine learning. Now, machine learning, quite frankly, was pretty awesome because for the first time, humans could take features from a thing. That thing could be language, it could be images, it could be data. And they could take features from that thing, perform what's called feature extraction, teach a computer in the form of an algorithm what type of features the computer might be looking for, and then on its own, it could find those features. Now that's pretty cool because you could teach a computer what, say, a couple different types of words are, and it could identify other words. You could teach it a little bit about what, say, an animal looks like, and it could find other animals. So that was a really powerful advancement when we start talking about artificial intelligence. But as we're going to see when we go through this presentation, it has some limitations, and we're going to discuss those. Around 2010, we saw the rise of deep learning. Deep learning is an incredibly advanced form of artificial intelligence. It really got its kickoff at a Toronto deep learning conference in 2010. And this was where one of our co-founders, Dr. Eli David, started putting together the framework and the idea for an artificial brain to essentially solve cybersecurity. And then, of course, with our other two co-founders, Guy Caspi and Nadav Mammon, we got the ability to put together Deep Instinct in 2015. So deep learning is an incredibly advanced form, as I mentioned, simply because for the first time, computers learned on their own. No longer were they required to have features input into them from a human. We could simply build a neural network, we could point it at a data set, and as long as the data set was good, and as long as the humans understood the data set and what would come out of it, the neural network could discover incredible correlations and capabilities of information out of that data set. This is what gave us the real rise of, say, self-driving cars. Because for the first time, a car could learn on its own what different obstacles were, even if it's never encountered them before, simply by falling back and utilizing its previous training. So as we go through, we're going to talk about how artificial brains do it and also how human brains do it, because they're incredibly similar. So let's talk a little bit first about classical machine learning. This slide here is really where every data scientist PhD begins their life. Can you classify the difference between a dog and a cat? It's a really challenging problem. If I were to give everyone listening to this video a pen and a paper, and I were to say, I want you to write down all the differences between a dog and a cat, you may struggle to do that. You may struggle to figure out what features you could write down from either one which would identify it accurately because they both have, four legs, fur, paws, they both have tails in the same place, ears roughly in the same place, they both have similar looking faces and how the skull is constructed. So it can be very challenging to figure out what features are unique to each one. Now, some people might say, well, cats have retractable claws, and that's a true statement. But the challenge there is that when they're retracted, thus identifying them as a cat, that's a hidden feature. The computer can't see it, doesn't know how to process something it doesn't know about. And when they're deployed, once again, the feature is a claw at the end of a paw, there's four paws, they're furry, and once again, they kind of look like a dog from a feature perspective. So this is a very complex and challenging problem. But of course, data scientists are very smart people. This has been solved, and computers can do this with a fair amount of accuracy. And they do it through, as I mentioned, feature extraction. The human will sit down and start pulling out all the features. We're talking about sizes and distances and ratios, everything that a human can think of that can identify a dog or a cat independent of one another. The problem is this: what happens if features are just too similar, right? So, is it a blueberry muffin or is it a chihuahua? This screen right here would be near mission impossible for machine learning, simply because the features are too similar. Now, this may be a bit of a silly slide, but as you're looking at it right now, your brain is able to identify dog and muffin without too much of a challenge. This is something that a human brain can do because of your training that a computer simply struggles with. But let's kind of simplify this slide a little bit and talk about it. So here's a similar example. When features are simply too similar, a computer really struggles with something like this. This is why when we start talking about cybersecurity, even powerful machine learning tools have very high false positive rates. They tend to err on the side of caution. So to give a classic example, there are remote administration tools used all over the world by IT departments, by SOCs, etc. And they communicate with end users, they install drivers, they maybe reset passwords. They're perfectly legitimate tools that are used legitimately. But of course, then we have what's called the malicious RAT, the malicious remote administration tool. This is a bit of a challenge because it also has the same capability. It can communicate with the end user, it can push and pull files, it can perhaps keylog or keystroke, it can export this information. It can do a lot of things that look really similar to that legitimate administration tool. So many of these tools, cybersecurity tools, that are based on machine learning will classify that malicious RAT as malicious, as rightly they should. Unfortunately, they will also classify that perfectly legitimate administration tool as malicious. That's a problem because that starts generating false positives. So a lot of these tools, as I mentioned, tend to err on the side of caution when they don't quite know what they're dealing with or when something looks too similar to a malicious event. Now, that may sound like a good idea. It may sound like, well, wouldn't you want a security tool to do that? Ideally, I would say you'd want a security tool not to make that mistake in the first place, but false positives really are very impacting to a company, simply because I'm just going to use some very low but general standards. Let's say a company has just 30,000 events a day. Now, most companies would love to only have 30,000 events a day. But at 30,000 events a day, and even just a 1% false positive rate, which to a person sounds really low. But when you start looking at that, you are talking about hundreds of false positive events. But of course, you don't know they're false positives. Humans have to investigate those utilizing their EDR. So they begin to investigate, even saying just a 10-minute investigation time. We are talking about hours and hours and hours of a full-time employee simply chasing ghosts around the network. Now, that's not very operationally efficient. I'm sure most companies would want to take that employee and utilize their exceptional skill set to perform projects or do optimizations, roll out special capabilities with the network. But these are things they can't. So not only are most companies kind of strapped for talented cybersecurity workers, but unfortunately, then they're spending a lot of their time chasing down false positives. So lowering that false positive rate can be incredibly beneficial to a company. But believe it or not, this screen, misleading features, this actually isn't the real struggle that machine learning has. This one is. When you start getting into hidden features, or noise as we call it, this was something I mentioned earlier when I talked about the retractable claws. When they're not visible to a machine, the machine has a hard time figuring out if they should be there, why should they be there. If they're not, it'll simply ignore it. When we start talking about machine learning, I mentioned in the 1980s, we saw the rise of being able to talk to a computer and advanced image recognition. But I think we all remember the old TV shows from the 80s and 90s or early 2000s, where all you had to do to beat facial recognition was put on a hat and sunglasses. And suddenly the computer didn't know what to do. And why? Because you were removing the features from the computer's ability to process them. When we start talking about things like self-driving cars, machine learning could never bring us this technology for one very simple reason. Let's say a machine learning car is approaching an intersection and there's a stop sign up ahead. But unfortunately, there's a bush growing in front of it, or perhaps there's a car parked in front of it. So you only see the top half. Maybe you only have a couple angles up top and the tops of some letters. Well, when so much of the information is missing, the machine learning simply wouldn't identify it as a stop sign and it would roll through. Now, of course, you could change the algorithm and say, okay, let's err on the side of caution. And let's say if you see anything that matches even remote images of white letters on a red background with a white border with even a couple angles, that it's a stop sign. Think about the false positives this would generate. Anything from a person wearing a hat or a shirt to a sign hanging off the side of a building could all confuse the car if it had just enough of those features. But of course, a human brain isn't fooled by this scenario. Everyone listening to this will stop at that stop sign, even if you see only 10 or 15% of it. You will stop at that stop sign, even if there's a car parked in front of it, so you only see the top half. So will autonomous vehicles powered by artificial brains, powered by deep learning like we have today. So the cars that you see that are driving along on their own, or the delivery trucks in some countries that are making their routes, those are all powered by deep learning. And one of the big powerful things here is something I always like to instill in anyone that listens, which is the power of artificial brains and deep learning is like a human brain. They understand context from incomplete data. That's a really powerful feature when we start talking about lowering false positives and improving accuracy. So, to kind of recap quickly, the real big challenge we see in machine learning is that second step right there, manual feature engineering. Anytime a human is responsible for figuring out the features, anytime a human is responsible for writing a linear algorithm, there's going to run the risk of both not including features that are important or perhaps generating false positives. But deep learning, of course, doesn't have this problem. Just like a human, they consume 100% of the raw data. So the way we kind of like to explain this, of course, is when you were very small, you were learning what dogs and cats were. And your parents wouldn't perform feature extraction, or your teachers, they would just point to a dog and say, that's a dog. Or they'd point to a cat and say, that's a cat. And over time, you started developing the framework for what was a dog and what was a cat. Today, I'm willing to bet that you are a world-leading expert on the identification of dogs. I'm willing to bet you have around a 0% false positive rate with around a 100% efficacy rate. And of course you would. Why wouldn't you? You've seen a lot of dogs and cats in your life. But the cool part is that at one point in your life, again, when you were very small, one day a poodle walked in front of you. You'd never seen that before. Now you've seen other dogs, but for the first time you saw a poodle. But I'm sure you looked at it and you said, hey, that's a dog. And no one was really amazed by this. Your parents didn't step back in awe and amazement and say, how could you possibly have known that? That's a 0-day dog. No, because that would be silly. Instead, everyone said, yes, that's a dog. Now, you didn't know the word poodle, so you were then taught that word. But the point is, you were able to identify something that you had never seen before accurately simply because of your previous training. Artificial brains can do exactly that. And that's a really important distinction. They can understand context from incomplete data. So, deep learning, let's talk about it. Why is it called deep learning? Why are these things called artificial brains? Simple, they kind of look like a brain. If you break out the math and look at the math, what you're going to see is that just like a human brain, artificial brains have neurons, they have synapses, and that's what helps them build contextual information. Because again, just like a human brain, they have the ability for all answers and all questions to touch each other. This is much more powerful than a linear model. So it's why when you see a candy bar at a store, you might think of that corner store that you grew up near as a kid. And why? Because you have different neurons and synapses connecting those memories together. It allows you to identify things. Well, artificial brains can do the exact same thing. They can see and understand brand new experiences, brand new, in our case, malware, even if they've never been trained on it before, because all their different training connects to each other. So how do we build this? First of all, it was developed entirely in C and C++. That's really important, simply because it means that we have a very robust framework. We do optimized GPU training. Of course, we have to use GPU. We have about 100x the capability of a CPU. And of course, one of our primary early investors, NVIDIA, helped us extensively with our neural network and the hardware that powers it. And of course, it must be efficient. That has to be the begin all and end all. If we were to take our artificial brain and deploy it on a phone or a laptop, and it were to run up the processes, run up the RAM, run up the CPU, and crush that machine, well, then we wouldn't be operationally efficient. So it's very important that we have a very lightweight agent that resides on endpoints to ensure that it's efficient for our customers. So again, the benefits of deep learning cannot be overstated. Zero time detection and prevention. That means the artificial brain is operating pre-execution in less than 20 milliseconds. So we're not an EDR. We don't need a human being to click on a thing. We don't need a bad thing to begin before our artificial brain begins examining it. The ability to operate on any device, any operating system, the ability to process on any file. These things are really important. And more importantly, perhaps most importantly, it must be connectionless. The artificial brain resides on each and every asset. And the reason that's important is because there's a lot of times that an employee is away from the protective shell of their corporate environment. They're away from those big expensive firewalls. They're away from those IPS devices. They're away from the other tools. Maybe they're at a coffee shop. Maybe they're on an airplane. They have to be protected round the clock, zero time, all the time. And again, I definitely want to talk about some of the challenges for end-to-end deep learning. That top one, really important, okay? Using an off-the-shelf open source framework is incredibly challenging. And we see it now. There are companies trying to get into the deep learning game, cybersecurity companies trying to get into the deep learning game. And what happens? They're using open source frameworks, and the end result is that their product really doesn't have the full efficacy, or perhaps it's running a little slow. And that's because it's important to build these things from the ground up. It's important to custom design the framework, which I mentioned at the top of the presentation is something that Deep Instinct has, and we've patented. But the reason it's important to use a cybersecurity framework is simple. When we start talking about something like TensorFlow, which is Google's open source tool, TensorFlow is great at image recognition. That's what it was designed for, and it does an absolutely phenomenal job. The thing is, though, with images, you can manipulate them. If you get a 1 meg image in or a 5 meg image, you can resize them so that the artificial brain understands, or that the neural network can comprehend it. You can even adjust for format if you need to. But with cybersecurity, you can't do that. Files are going to come in as they come in, and they're not going to be adjusted. A PE file isn't going to be resized. We're not going to lose pixels in a TIFF file. We're not going to resize a PDF. And if you can't do that, then suddenly a framework designed for image recognition becomes less effective. So of course, having a framework that doesn't care about size, that doesn't care about any of those parameters, or rather one that can adjust dynamically to them, is much more powerful and important. And then that bottom one, the scarcity of deep learning experts. A lot of people ask who we compete against, and I always kind of chuckle and say, well, think of the biggest companies on earth. They're actually our competition, especially for talent. Because when it comes to deep learning scientists, they're tough to find. So it's important that we have the ability to both hire and retain those really, really important data scientists that have a mastery and a capability in specifically deep learning. I also want to talk a little bit about something I mentioned earlier, the neurons and synapses. So what they're called in the deep learning world is hidden layers. So this is a real example. I know it looks like it was created in Microsoft Paint, but I promise you this is real output. So I do want to talk about how hidden layers affect discovery. So here we've got our scenario. We've got our red malicious files and our green benign files all within our environment. At just 3 hidden layers, it's terrible actually. It's pretty bad. You see how many malicious ones it missed located in the blue. You see how many benign files it classified as malicious, which are the green files located in the white. 3 hidden layers really doesn't get you anywhere. We're gonna have to do a lot better. So if we double them to 6, it does better, but it's still pretty terrible. Sure, we've cut down on the false positives, that is the number of green benign files within the white, but look how many malicious files located within the blue that it missed. So even at 6 layers, you're still not doing too good. But when you start getting up to around 20 hidden layers, suddenly the brain becomes technically perfect. It successfully finds, classifies, and identifies all of the malicious files, or all of the malicious bits, if you will, and it does not call malicious. It successfully weeds out all of the benign. This is something that's really important. So how many hidden layers does Deep Instinct have? Well, that's a bit of a state secret, but it's more than 20. But this is kind of what we want to show, simply because the more layers you have, the more powerful your deep neural network, the more technically perfect the artificial brain is. And that's true across the board, whether it's self-driving cars or cybersecurity. And of course, as I mentioned, the more layers, the better the accuracy. Now, would we want to have 1 million hidden layers? Well, of course we would, but it takes a whole lot of computing power to do that. I'm not entirely sure there's enough computing power on the internet to power 1 million hidden layers, but the more, the better. And that's what our deep neural network, powered by our NVIDIA GPUs, are attaining. More hidden layers, more accuracy, more technical perfection. And it's also important to note that we didn't invent this. We're not the only ones using it. This isn't magic. It's actually around us all the time. So it's being used in natural language programming from Google, Apple, Microsoft, and others, speech recognition. It's being used in self-driving cars, as I mentioned. It's being used in logistics programs from Amazon for facial recognition with Facebook. These are things that power neural networks and artificial brains around the world. So how do we apply it to cybersecurity? First, we build the artificial brain, a static engine that is a pre-execution tool that is going to operate and detect and prevent threats in sub 20 milliseconds. So as any new write to disk is occurring, or as any modification on disk is occurring, the artificial brain is going to be looking at in real time all the time. But of course, we also have on execution capabilities. We're not content to rest on the laurels of the artificial brain. We have the ability to look at shellcode injection, to look at memory space. We have the ability to look at any type of process takeover. These things are important to continue to monitor a system to ensure that something even like fileless attacks don't get through. And then of course, post-execution capabilities. We have RCA, that's root cause analysis. We have our forensics ability. We have the ability to classify the malware in 50 milliseconds or less, so you know exactly what you're dealing with. We also have remediation capabilities in the form of whitelist, blacklist. We can import lists. We also have network isolation capabilities. So we do all of this to bring our customers a holistic approach to cybersecurity so that they can rely on our product no matter what the attack might be. So here, I do want to show a real world example. We have dozens of these examples. I just happened to pick the Crisis ransomware because I like it. So let's talk about it. 2018, Crisis, a brand new ransomware family comes into the world. Now, what does it take to be a ransomware family? Simple. You have to attack a computer in a new way, but you also cannot use borrowed code. So there's a couple 100,000 different malware families that exist in the world. But of course, we know that there's hundreds of thousands of variants and mutations that are made every day based off these families. But Crisis was a brand new ransomware family. The world had not only never seen it before, but they've never seen anything like it before. So about 2 months later, It was discovered by researchers and uploaded to VirusTotal, where it was missed. It was missed by pretty much everybody, not just the legacy guys who didn't have a signature for it, but of course they wouldn't. It was also missed by the next generation machine learning tools. And why? Because their algorithms did not have the feature set of what crisis was. So what happens when everyone discovers a new piece of malware? Well, they take the hash and they start scouring their logs to see if it exists in their environment. Of course, one of our customers did find it actually the day before. It attempted to enter the environment. It was writing itself to a disk. The artificial brain saw it in sub 20 milliseconds, prevented it, killed it, and it never executed, never got a chance to get a foothold. That's actually not the interesting part of this story. The interesting part is that the artificial brain that did this was 14 months old. That's 14 months without a single update, because remember, we never update our brain. We produce a new one once or twice a year, but we never update an existing one. So that's 14 months ago was the last time it was ever trained on malware before it was released into the world, because we also never train on customer data. So 14 months ago, without heuristic updates or database updates or cloud updates or anything like that, 14 months ago without any algorithmic changes or algorithmic model changes, because we don't do that. So 14 months ago was the last time it learned about malware. And yet, when crisis, a brand new ransomware family, without using borrowed code, without using or attacking a computer in a new way, the artificial brain saw it, identified it, and stopped it within 20 milliseconds. That is what deep learning is doing for cybersecurity. So thank you very much. This concludes our presentation on machine learning versus deep learning, and look for more in the future.